Good morning, ladies and gentlemen. We're going to talk about the Sheffield Rotherham UK pilot tram train project. I'm going to start. I'll hand to John later on to talk about some of the challenges. I'm going to give an overview of the project, what's been done to the infrastructure, a very brief overview of what the vehicle is, and then go into some of the detail around some of the challenges. More on the infrastructure side. There's been a lot more challenges along the way, but I'd limit it for sort of the infrastructure side. And then just a quick overview of testing, commissioning, and where we are going. Tram train, it's a vehicle that can operate as a tram on the tramway, another train on the railway. It's trying to provide a seamless journey for the passenger. They should not even know whether they're on a tramway or a railway. It's also trying to provide better links, so it's trying to connect suburban areas directly to city centres. Avoiding going to the heavy rail station, connect onto a tram or having to then walk into city centre. It's trying to provide faster overall connections by being a bit slower. It's also trying to use existing infrastructure, better use of existing resources, trying to replace some of the local services from heavy rail, freeing up capacity for longer distances, higher speed services. In the UK, the technology has been around for quite a few years. The first one started in Carroll in Germany in the early 90s. It's developed into several locations in Germany, some in France, some in the Netherlands. The project was challenged by the Department for Transport in the UK to actually introduce the technology to the UK. There's been steps on the way. The Tinsley metro system had a light rail vehicle operating on heavy rail, but that's basically just a light rail vehicle operating on heavy rail, still under signals on both sides. There's no line of sight operation. It's also limited the operation of the heavy rail infrastructure, with double blocking required, so you've got to put speed limits on, you've got to put additional spaces around either side of the system. There's two safety systems overlaid on top of each other to try ensure that the trains don't come into contact. The actual challenge for the UK pilot was trying to reduce those limitations and actually develop the learning to actually be able to allow the service to operate, or tram train to be operated wider within the UK. So the actual pilot goes from the centre of Sheffield at the Sheffield Cathedral on the Supertram system, along the tramway to Meadowhall, and then connecting onto the heavy rail system, the network rail system at Meadowhall, and then running along into working with existing freight trains, passenger trains, to a new tram stop at Parkgate. Parkgate is a shopping centre, retail park on the outskirts of Rotherham, which had its railway station shut in the 60s. So it's trying to provide additional services from Rotherham into Sheffield, sort of trying to connect passengers with centres of employment within Sheffield. The project is funded by the Department for Transport with project partners of the South Yorkshire Passenger Transport Executive, who sort of led the procurement of the vehicles and managed the overhaul project, Network Rail managing their infrastructure, and the Sheffield Stagecoach Supertram being the operator and maintainer of the tram system. So in terms of what we've actually carried out, on the tram system, to be honest, the vast majority of changes would have been required for a new tram anyway. So as part of the service, we need a new tram. As part of the actual, I'll come on to the vehicle later, but the plan was also to introduce additional trams anyway. So most of the changes, such as signalling system, the depot upgrade, would have been required for a new fleet of vehicles. The only sort of part that's been required specifically for tram train has been around the rail replacement and guardrails, which I'll come on to later. On the network rail side, we're talking about 6 kilometres of the route that's required 750 DC overhead installation, two new low-level platforms, or 2 low-level stations, plus the connections at either end into the turnback side and at Parkgate, and the connection onto the network, onto the Supertram system, along with all the other changes required, signalling, etc. The connection between the two systems is what's known as Tinsley Chord, which is a cord that runs off the tram system onto the network rail side. It's about 400 metres long in an S shape, with a 25 metre radius curve at one end, an 80 metre radius at the other, and then a much shallower curve as you go onto the network rail system. The actual connection has been constrained by the geography as to where it is. It does occur right under the Tinsley Viaduct, which is, for those not in the UK, is the main motorway, dual track viaduct for the main motorway between Leeds and London. The vehicle that has been introduced, it was bought from what was originally Voslo, which changed to Stadler in Spain. It's a pretty standard tram-type vehicle. The CityLink family, which is also had been supplied to Carroll in Germany and also Chemnitz in Germany. Maximum speed of 50 miles an hour on the tramway, 60 miles an hour on the railway. The key parts that make it a tram train are that it does have additional crashworthiness features compared to a tramway vehicle, but also has the additional safety systems, TPWS required for operation on the heavy rail system, along with the communication GSMR required for heavy rail as well. One of the the unique features to the vehicle for the UK was that we actually had to put in a switch that changed between a tram and a train. To best meet the railway group standards, there's various features that have to change, one of which is the radio system, so when you change over, you change which control centre you talk to. But other things that have changed have been the sanding system and the lighting configuration. When operating on the road, you've got to have dippable headlights so that you can operate legally on the road, but it's also to try and best meet the railway group standard for visibility on the railway, so that the tram can be seen at the distances for our track workers. We've actually altered the light setting, so using the same lights, but altered the setting so that during the day it uses the main beam, but at night it uses dipped headlights, and the tail lights use the brake lights on the railway permanently, just permanently on, just providing the maximum visibility in the rear. So that's basically an overview of the tram train project. What I'm now going to talk about is some of the challenges that we've encountered along the way. The first one is the wheel rail interface. One of the key features that we knew from the start of the tram train was actually the wheel profile to be used. The tram profile, the existing tram profile, would not be suitable. The key reason for this is the flange wear clearance difference between the network rail system and the Supertram system. The flange rail clearance is between the check rail and the running rail, so this distance here. Due to different construction philosophies when the Supertram system was installed, trying to minimise the clearances on the in-street section, a distance of 32 millimetres was chosen to match the tram profile that was in use at the tram profile that was used. Whereas the network rail standard is a clearance of 42 millimetres. So if you try and use a tram profile on the network rail infrastructure, you will end up with the tram wheel profile that should be going along this route, potentially changing over and going along the other route, possibly the other way around, but possibly leading to derailment. So that was one of the challenges. The other one is all the different profiles used. So on the tramway, you've got embedded grooved rail installed vertically. You've also got Vignole rail 39E1 installed both vertically and 1 in 40 inclination, whereas the heavy rail side, the network rail side, uses 56E1 inclined at 1 in 20. It's trying. In addition to that, there's actually a sort of a different design around the switches used. So the tramway switches are sort of an undercut switchblade, which is not sort of which is a standard sort of switch used in Germany for railways as well as tramways, but it's not something that network rail use. So there's actually one of the key challenges with actually finding a profile that has can manage both different flange wear clearances, the different switchblades, as well as the, then trying to minimise the wear and rolling contact fatigue on the different rail profiles. So this is where we've got to. So the two different the actual profiles that you start with is the tram profile. So you've got your flangeway clearances that the thickness of the flange is actually designed for. In addition, the actual depth of the flange is only 24 millimetres, which works fine on the tramway switches, and also is much better when you're actually running in grooved rail. However, on the network rail system, 24 millimetre flange depth has become the derailment risk on switches. The minimum flange depth on network rail is 28 millimetres. The actual P8 profile actually has a 32 millimetre depth. But then you've also got to allow for the thickness of the flange. In addition, Sheffield has some flange running diamonds, so you've got to have a reasonably flat flange tip. So putting all that together, using what is now the University of Huddersfield Institute of Rail Research to design the profile, it's basically coming up with a big compromise around the profile that's being used. Sorry. So what's been used? You end up with a step in the flange back. So that on the tram system, you can use the existing check rail clearances at a level with the rail. But on the network rail system, you've got the same thickness as the P8, but it's actually raised up above the running rails. This actually then gives a requirement for having raised check rails, which is not common within the UK. We're also, because of the ensuring the derailment risk on switches, we also need the 28 millimetre depth of the flange. And then the profile, the flange angle is all largely based around the P8 rather than the tramway, because that was basically found to be the best compromise around minimising wear and rolling contact fatigue. Having sort of this step flange back is nothing really new for tram train. The Carroll has a similar sort of arrangement, all tram trains normally do. It's also, to be honest, not that different from what's in the UK. Manchester Metrolink have a similar profile with that sort of arrangement and the use of raised check rails. There are some consequences to this. As I've mentioned, the raised check rails, this is a picture of Metrolink. So Network Rail have had to seek a deviation to install raised check rails on their infrastructure. As part of that work, we've had to carry out a full analysis of gauge clearance on all rolling stock that could potentially go down that route. That is pretty much gauge clear. One of the other consequences is that we've actually had to ban wheel skates. The wheel skates in use in the UK were not designed around raised check rails, so they've actually been banned on the network rail system on this section. That is one thing to be taken into account if anybody's having to do tram train elsewhere, is that the consequence of banning wheel skates and whether a new wheel skate needs to be designed to become, for the limited route that the tram train in Rotherham, Sheffield's operating on, is not a major issue because there's plenty of diversionary routes around. Other places there may be additional issues. The other issue is that on the tram system, we have guardrails on the bridges that's actually only mounted alongside the running rails, and we've had to mill those in situ using a rail milling plant just to give the gauge clearance for the flange back. But the more significant change that's been required has been rail replacement of the tram system. The original grooved rail profile was had a shallow depth for the groove, which with the additional flange depth of the wheel, it has resulted in some significant requirements for rail replacement. If the rail was all new, it would be less of an issue. The tram system's been in 25 years, with sort of where you'd expect for 25 years of use. So we've had to undertake, I think within 2013 to 2015, we've undertaken 10 kilometres of embedded rail replacement, and we're now undertaking another 10 kilometres this year and over the next couple of years. It was interesting to see Werner's presentation on how Werner Linen have manage their rail replacement plans, because in Sheffield we used a very similar process around basically modelling the wear rates and understanding which sections are need to be done over the next 20 years. One of the issues that we had actually was more around the data that we have is not continuous and is very sort of targeted at specific curves. Having a continuous measurement system on a vehicle that Jennifer talked about is something that would be much more useful for having modelling rail replacement in the future. I'll now hand over to John to talk about some of the other challenges.
Hi. Yeah, obviously Rob's talked about the track side of things. I'm going to talk more about the platform interface and the overhead line. One of the key challenges we had with the platform, the Supertram network, unlike Manchester, uses a low-level platform, so we're sort of 370 mil above rail level. And obviously with light rail standards, we can have no more than 75 mil a step. Obviously network rail, you've got a step this big. So we've got some big issues. The biggest issue was if you actually built the platform to suit the tram, when a W6 comes through, it rips its front end off. The two weren't compatible, so trying to fit a square peg in a round hole. So obviously the problem that we've got, you're trying to go back to square one. How do you make it compliant for both, still conform to the 75 mil? So what we ended up doing was we had to convert the track into high track fixity. So obviously what the maintainer didn't want, the platforms are only 30 metres long. So what they didn't want was a 30-metre section of slab track, because obviously that causes problems with bolting onto the southern end of an existing station. So that creates problems with maintaining the track into that area. What we ended up coming up with was, if that's the right button, no, that one, there we go, is basically a concrete block. The idea being that actually locks the track and stops it moving. So what you essentially had was a steel plate and elastomeric bearing up against the end of 3 sleepers, concrete block up to the riser wall of the new platform wall, and then locking the two tracks together is one continuous timber through bearer across both roads. That way it gave the maintainer flexibility that if he needed to come through and tamp, he can literally just pull the block out, so he can run the tampers through, but locking both roads together gave us that high track fixity. Being able to do that, we ended up being able to design the track so that with, full wheel wear with full deflated suspension, we were at a maximum of 70 mil of stepping, so we were within the tolerances. We literally had massive spreadsheets working out every single different option to try and make the thing work. So onto the overhead line. The area, this was Rotherham Central Station, which is about halfway up the job. This was back in 2007. Believe it or not, there is actually a railway under there, under about 2.5 feet of water. So obviously front protection, particularly for a brand new feeder station, was quite important. So the feeder station had to be designed for what they call N-1 standard, which means that the maintainer wanted 2 completely diverse electrical supplies. So if one ring main went out, they could still run the tram train service. As a consequence, that meant then that the maintainer also wanted N-1 inside the feeder station. So normally on a light rail system, you'll have 1 transformer rectifier. We've got 2. So everything is doubled up. There's a backup on a backup. So that allowed then that, if they needed to do routine maintenance, they could take half the feeder station out, run the other section, keep the tramway actually running. Obviously, the other problem then that we had is this feeder station at the cost of about £2 million potentially is sat underwater. So we had to look at ways to elevate it, comply with the EA rules and regulations. Obviously, you can't just put a load of fill in there because then you're taking away flood alleviation areas, etc. The other issue we had as well with the feeder station, we went to Northern Power Grid. They could get us the 2 11 kV high voltage supplies that we needed to feed the overhead line. What they couldn't actually get us though was the low voltage supply to do all the lighting, the heating, maintain the breakers, run the SCADA systems. So as part of the system, and the next slide will show you how complicated it is, we ended up building our own mini feeder station to feed the feeder station. It's the only way we could do it to get the power supply in that we needed. With this scheme, the SCADA system was originally going to be run and managed by Sheffield Supertram over at Nunnery. About 12 months before we commissioned, something like that. The job's due to be commissioned, or first services in a week and a half, something like that. Network Rail decided they're not going to let Supertram control it, York ECO are going to control it. So all that work that we'd done on all the SCADA systems and everything else, we had to redesign, is the politest way to put it, and recontrol it all through to York. So this is an area that is literally about 45 metres long and about 8 metres wide. That is the power supply for the whole overhead line system. So you've basically got what looks like a house, which is the DNO supply. They wanted a full brick building, it all had to be elevated so that we didn't get any flood protection, anything like that. That's got the two main high voltage supplies in. We've then got the main feeder station itself, which has got its high voltage switch gear, its DC switch gear and all the SCADA gubbins and all the rest of it that's in there. And then this over here is our little mini substation. So literally the power comes out of the DNO into the feeder station, high voltage out the feeder station into what we call the LVAC, which is the low voltage AC system, through its own transformers and then back into the feeder station and back into the DNO supply to feed all its own breakers, switches, backup supplies and all of that type of thing. It's the only way we could do it because there was no LV supplies. So that created quite a few complications and quite a few iterations. So how do we get over the flood potential? That's the DNO building. So that's the house that I was talking about. Normally that is ground level. And obviously these are dug into the ground. So your incoming HV cables are all below ground. All we did was we picked it up. So what's normally the entrance bay down here, we just sat it on ground level. Then when the ducts come in, we just put a berm around it. No major redesigns, no major rethinking, just took the standard design, tweaked it a little bit, just lifted it. The key one though is the feeder station. So that's the main block, about a 40-ton unit, about 2 million quid in there. This was originally going to be 1 metre high. That's all we needed for floodplain. Then the maintainer came along and went, can you make it 1.5 metres? Because it's easier for me to get in to maintain my cables. Then we designed the foundation system, which actually is a series of 10 piles with basically what looks like a standard OLE transfer plate. So by the time you add that on, we're now about this high. So we started off down here, we ended up there. Just the way the design developed. That's the LVAC building. So that's the transformers down. They're your two transformers on the back. Just showing where we're actually transforming everything through to get our low voltage. A couple of photos of the internals. So they're all the 11 kV breakers. There's all the DC switch gear. So obviously with the kind of the feeder station split into two sections. And then that's all the SCADA system and various other electrical gubbins. I'm sure any electricians in the room will be knowing exactly what that is. I'm a civil engineer. Overhead line. So obviously the main complication we had with this is there's never been an overhead DC system on network rail. Doesn't exist. So there was a lot of backwards and forwards early days in the project. So sort of circa 5 years ago, we started talking about this. There was also all sorts of talks about, well, we'll use the Supertram system. That's obsolete, so we can't use that. We'll use Siemens SiCat. No, we don't like that. So what that basically is Network Rail Standard Series 2. So any overhead line engineers in the room will know exactly what I'm talking about. It basically looks like Series 2, but it's not. There are some fundamental differences. So obviously the problem that we've got is with the DC system, there's no traction return. Obviously with the AC standard network rail there is. So we've got the issue of the double insulation. So all tramway systems are double insulated. So if one insulator fails, your second insulator is your backup. Obviously with this, there was no backup system. There was no second insulator. Obviously Network Rail, as far as their product approvals, they wanted full product approval for this. Even though it's taking a standard Series 2, because we're putting DC through it, they wanted a whole new design range. So we've produced, or Mott McDonald's on behalf of Carrillion, as we were, have produced the new standard series range. They've produced all the new green books, and obviously we've had a lot of brand new bonding designs to go through for the project. So how did we do it? It essentially follows the same format as a tramway system. So AC systems, you've got your standard 2 insulators in your SPS, your small part steel. And then what we've done is we've added an insulator into the castle and an insulator into the registration arm. The original plan was actually to take the standard network rail insulator and redesign it as a twin, because the thing's about this long. So it gives you plenty of space to design a DC insulator. Believe it or not, a 5p carrier bag puts scuppers to it. The maintainer gets a lot of problems where carrier bags get wrapped around the insulators and it bridges. When it bridges, it trips. Well, obviously with our system, you've got no traction return, you don't trip. So the problem is, if a track walker comes down here and leans up against the mast, there's a carrier bag on there, he starts shaking a little bit. So what we've ended up doing is, because of that, the network rail standard says you need 600 mil of separation between 2 live components. So that's why we've ended up with the insulator in the castle and the insulator in the registration arm. So they're brand new products designed by Bonomi on behalf of the project that are now part of the new DC Series 2 catalogue. The other thing we had to do as well, feeder stations on a tramway system are normally about every 4 kilometres apart. With the nature of the tramway project, excuse me, the northern end of the job is about 2.5 kilometres from the feeder station. So we're right on the limit of what the feeder station can give us. Well, we're actually too far for what the feeder station can give us. So we had too much voltage drop at the Parkgate end of the job. So what we ended up doing is putting in what we call the third cable, which essentially is an ATF cable in the principle of network rail overhead line. Jump it onto the catenary wire, every 300 metres. It's basically designed as a high power feed. So it's designed to help us get the voltage to the north end of the job. Again, the problem is there's nothing to actually hold it up. There's no design, there's no insulator, there's nothing in the network rail range. So again, this was designed as a brand new twin insulator by Bonomi specifically for the project. So there's been a lot of new and novel stuff that we've had to do for the overhead line. Just a couple of photos there of the equipment going up. So we used the SRS for actually doing all the wire runs. We had 10 disruptive possessions, 29-hour possessions, to get all the SPS up and get all the wires run out, contact catenary and third wire. We hit every single one, all the wire went up to plan. Don't get me wrong, we had to come back and do a lot of fiddling around, but we got the wire up. We also developed new slinging arrangements for all the overhead line to make it safer, make it more stable. Obviously there are just a couple of photos of the guys putting in third cables. So testing and commissioning, we split it into 2 stages. So we had stage 1 was the main overhead line, getting that energised, getting it commissioned, getting the system ready for Rob and his team to actually start testing the new vehicle. Because obviously once we built the network and the trams could run, Rob and his team had got 3-4 months of signing vehicles into use, driver training and all of that type of stuff. So we got 90 site acceptance tests we had to do. That was all the electrical testing in the feeder station and the overhead line. 138 designs that we had to get signed off as built correctly and ready to test the infrastructure. And then we got 7 signalling commissioning stages as well on top of that. One of which was the design of the system was changed to use axle counters from standard track circuits. The guys reckon in one of the relay rooms, because it's all old-fashioned relay interlocking, they ran 250,000 metres of cable to redo the interlocking for the reset restore on the axle counters. They were in there for about 3 months. It's soul destroying. Second stage is in October. As we've said, the vehicles are in final test at the minute. We driver training. The first passenger service will be next week. So we are very, very close. And again, so in addition to all the stuff we did for stage 1, there's another 29 site acceptance tests to do, 3 signalling stages, and a further 81 designs that all need signing into use by the engineering team as part of the project. Just over to Rob for talking about the vehicle.
So as John said, as on I think it was about the 5th of May this year when the infrastructure was fully commissioned and signed off, It then handed across to us to actually carry out compatibility testing with the vehicle and some other testing that was also required. So on, I think it was Bank Holiday Monday the 8th this year, we got out for the first vehicle out onto the network rail system. So the testing carried out has been gauging, checking that the overhead works, checking all the clearances, checking the stepping distances, checking that we can recover the vehicle as well. So we got a locomotive there and pushed it backwards and forwards a few times. Just checked that all the emergency couplers all worked. One of the, as John's gone through the traction power supply, we also did quite a lot of traction power testing to prove that there's, with the full service running with additional vehicles, there'd actually enough traction power down there as well. The maximum speed on the tramways are only 50 miles an hour. On the network rail system, although the vehicle is capable of 60 miles an hour, it's actually 55. So we actually do some of the vehicle commissioning tests again, just to get the higher speeds. So we actually loaded the vehicle up with what's actually Harris fencing feet as ballast weight to load it up to the full capacity of the vehicle. So that's actually 20 tonnes of Harris feet there to allow brake testing, ride quality testing on the infrastructure as well. So testing took about 9 weeks. There was actually a space of 9 weeks. It actually took about 4 weeks overall. It's just that the availability of the infrastructure was limited to 4 nights a week, 4 hours a night. There's several weeks you can't get to because of diversion routes for other maintenance activities going on. And then we lost a week of testing for network rail finishing off snagging. And then we also lost 1 night due to cable theft. So, and then we also lost another week due to the tram drivers going on strike. So there was quite a few challenges chucked in the way, but we did manage to get it all tested, fully commissioned, ready for the 15th of July, when we actually started driver training. So the actual drivers being used are tram drivers, existing tram drivers, who have all had medicals to prove that they're actually safe to be able to drive a tram, i.e. they've got colour vision. Tram drivers don't need colour vision, but you do need it for the heavy rail system. The tram drivers were then had about 2 weeks training course. So the training that's been carried out has been limited to the infrastructure provided. So there's no level crossing on the route, so they don't get trained in it. So they are a limited range, but they are fully trained drivers for this route. Overall, I think there's 24 drivers been trained for now. We are training about another 4 or 6, just to provide some flexibility in the future. We expect some of the drivers will probably leave within 6 months and move to Northern or something like that, but that's what tram drivers do anyway. So driver training was completed about the 14th of September, and since then we've actually been ghost running, so I've been running the full service, 3 trams an hour at approximately 20 minutes, from 6 o'clock in the morning to 11 o'clock at night. And that should finish, as John said, next week. There's just the final bits of paper being put in place. There's a final connection from Parkgate to the shopping centre at Parkgate still to be completed. I think it was completed last week, but it's not yet been fully signed into use. And then the original, when we started, when we agreed to this presentation, the original date was yesterday. So we were hoping it would be yesterday, but it's due to more political reasons than other. It's going to be next Thursday now for the start of service. Thank you for listening.